Okay, welcome everyone. A very good afternoon to you all. It is my pleasure to introduce and welcome our speaker today, Rosa Becerra, who's come here from the Instituto de Astronomía from Mexico City. Rosa started her academic journey at UNAM, doing her bachelor's in physics and then master's with a focus on astronomical instrumentation. She went on to do her PhD there in 2019. Her thesis focused on studying the electromagnetic counterparts of transients, transient events using robotic telescopes, in particular, using the facilities at the San Pedro Mártir National Astronomical Observatory. And for that work, she received the Alfonso Caso Medal. Nice. Then she went on to complete 2 postdoctoral fellowships, one at UNAM and one at the University of Rome. Over all this time, she has authored more than 40 peer-reviewed articles and getting almost 1,000+ citations. So her work is very well received in the community. More importantly, she's a member of the COLIBRÍ and the SWARM collaboration. So these are the 2 premier instruments at the cutting edge of detecting and studying transient events in our era. And she has extensive experience with optical and infrared telescopes that includes the GTC and the VLT. And she uses all these facilities to understand the transient events, including gamma ray bursts and their gravitational waves, and does all the theoretical modeling and observations. So today, we have the pleasure of hearing from her about this new and beautiful facility called COLIBRÍ. Thank you, Rosa.
Thank you, Romandy, for the introduction. And thank you very much for coming. So please, if you have any doubt, please interrupt me anytime. I don't care about the doubt. You are very welcome. So please tell me if something is not clear from my side. So thank you again for the invitation. I don't know where is my other host. Pedro, thank you very much for the capybara. Yeah. So first, let me introduce what is the transient sky. So I know that typically all the astronomers will work with galaxies, stars, something that we can study every day, every night, because every night are there. So we don't need, we don't have the hurry to catch light from there, because if I do the observation now or tomorrow or in 1 week, depends on visibility, but typically the event stays there. The difference with the transient sky is that these events are not always there. So basically, there are explosions that are coming by the death of the merger of compact objects. So if you see, for some seconds, some hours at most, typically here, for example, this new point appears for some seconds and compete in brightness with the galaxy that is hosting. So also here you see a new point and then it's fading in just some seconds. This is the transient, and I focus my work there.
Rosa, so I have this very stupid doubt in the previous one, in the XMM data. Is that the same observation and then on the right?
No, they are 2 different objects.
The point that appears and disappears is during the same observation. Or
no, they are
snapshots.
One is archive and the other is the new observation. So what is the general picture that we have? So here I'm going to show what is the one of the channels that we know that produce this kind of events. So the merger of 2 compact objects are able to produce these very energetic events. Why we know that they are energetics? Because as I said before, the brightness is comparable with the galaxy. And the duration is related with the size of the progenitor. So let me repeat, let me start again the video. Or not. So the component that you have to see here is, okay, we have the progenitor. You see the interaction between the gravitational field around, and it creates also gravitational waves that are highlighted here like blue waves. And here we have an electromagnetic counterpart that is typically a jet. What we do is we look for these kind of jets and we study the evolution during the first seconds, minutes, hours, days, depending on the progenitor. So, if you don't know where is the San Pedro Mártir, so it's another telescope, but San Pedro Mártir is here, 2 hours from Tijuana, so 2 hours from the border, and then you have to take the van in the observatory, and you go up in the mountain for hours, and it's one of the best places in this world to have an observatory. So the elevation is very similar to the Mexico City you have here, and we have a very good scene typically. And one of the most important things about our observatory is the percentage of nights that are good. It means that it's very valuable to put a telescope there. You are going to have a lot of nights good. So you are going to have very good photometry for the most of the nights that you can observe. Just to put this in comparison with other optical observatories, so we know that Chile has the best luck in the universe, but then the other 3 sites that we compare typically is Hawaii, that okay, maybe it has a better scene, but typically has worse weather because of the volcano. And La Palma, so we also observe from there very frequently, but the weather is not as good as in San Pedro Mártir. So our observatory is a natural, excellent place to make observations. So if you have the opportunity, you have to visit. So let me talk about COLIBRÍ. COLIBRÍ is a robotic telescope that is placed in San Pedro Mártir. We started operation 1.5 years ago, and it's a very small telescope. So the diameter is 1.3 meters, and the name is related, because we are common. So the name is related with the elegance and the velocity of the moon. So as I said before, the transient sky is something related with time. So we need to be fast, and we have to be able to get good photometry since the very first seconds after an explosion. For that was designed COLIBRÍ, and we can point any position of the sky in less than 20 seconds and start to take data. The instrument that is now mounted in the telescope is called DRAGO. DRAGO was designed and assembled in the Astronomy Institute, but for the very, very excellent group of instrumentation that we have. So this is, all DRAGO is Mexican, the telescope is French, and one of the PIs is William Lee. So here, of course, we don't see the sky like that, but the mount is very fast, and we observe every night. So I don't know. Well, the collaboration is French and Mexican. At some moment appears the flags. Yeah. So just to show you an image to understand the quality of photo that we can get for a very simple exposure. For the talks, I observe some of the Messier objects just to show how we can see the sky. So this is very beautiful image that we created with of course, with several filters in COLIBRÍ. So the animation is here. So what we do? We have this very beautiful instrument, and it was designed to follow up gamma ray bursts. Gamma ray bursts is the most basic transient after supernova in the history. Why? Because they are very common. But we don't want to do something that is very common. We don't want to do what is done for other groups. So we expanded our interest to also investigate what is more exotic or not well understood than GRBs. So typically, every night we follow not just GRBs, but fast X-ray transients, neutrino candidates, fast radio bursts, tidal disruption events, gravitational waves, cataclysmic variables, and X-ray binaries. So we cover all the transient sky almost every night. If you ask me, of course, there are time free to get observations using the GAT. Thank you.
So, do you look at the same place of the sky every night, or do you see news from?
No, give me 1 second. I think that is the next slide. No, it's not the next slide. But okay, let me. So every night we have a lot of events. So every night our planned observation looks like this, and the person in charge is Alan. That I know that most of you know him. So we have all the events, and all the person in the collaboration can propose some event that is interested, and also add what appears at that night. So we have, for example, this is a cataclysmic variable, this is a fast blue optical transient, this is a GRB, this is an X-ray binary, this is a supernova, Markarian, this is a tidal disruption event, and this is a fast X-ray transient. So we have to, we can observe all of them because we have a very good sensitivity. So at the end, we observe every event for 30 minutes, depending. So some of them are fainter, some of them are brighter. So we decide, of course, using the visibility plots and what is more important according to our priorities. And if you see, for example, this Markarian are the guest observer programs. So the objects that other people that are not in the transient groups want to observe, and we also dedicate time to that part. So as a member of the UNAM, you have the right to ask for observations, and you are going to get time and observation from COLIBRÍ. They are very friendly. So, yeah. So the first event that I want to show you, and this is an image that we took with COLIBRÍ. So this is a very, very high redshift event. This is one of the more distant explosions that we have ever catch. And we know that this explosion doesn't have a gamma ray counterpart. So it means that it's not a gamma ray burst as typically we see. So even if this was very, very, very far, the redshift is more than 5, we were able to follow up for more, for at least 4 days. So what filters we have? We have G, R, Y, C, and Y. We observe typically by default one in optical, in one near infrared, because it's more convenient. If you ask me about how many events we have every night new, the average is 2 days. Sometimes we have 5 the same night. Sometimes we have none in 1 week. So in average, because we cannot predict how the universe wants to behave every night. So what is more, what I want to highlight is COLIBRÍ, even with 1.3 meters, has been dominating the transient sky and the discovery of optical counterparts in this time that we have been operating. Why? Because we are able to point very, very fast, and even if the event is very faint, we are able to catch light, not just in blue, but also in red filters. It means that we are not constrained to something that is very close to us. We can also observe the early universe, which is amazing.
I have a question.
Yes.
That is like, for, no, in the other place. Yes. What do you prefer to choose? Do you prefer to observe the object just in the higher point, or do you prefer avoid that point?
That's interesting, and this is related with some instrumental constraints. For example, nobody wants to observe in the horizon, so we avoid this part. We don't want to see the floor. And COLIBRÍ cannot point to the zenith, is constrained, so we cannot point any event in this part. So yes, that's a very good comment. We typically prefer to observe with a better air mass, and also, yes, the more far away from the moon is here. So yes, we have a criteria to decide how we order these events every night, but this is Alan's problem, typically. So
about the previous, but the other one, yes, this one. So what's the the magnitude of this or the flux of this transient?
yes, it's around 18, but only in I and C bands.
The magnitude 18.
18, yeah, okay. Okay, so it's not so faint, but in case you receive an alert, let's say, of a transient event, and you, of course, you point, and how do you know that you will detect it? Maybe it's very faint, and you need to integrate more. Or how do you do that?
Because every group that works in this field have an automatic pipeline that compares the catalog with the image. So the idea is to make differential images always and to look for something new. So what is here? So this is the archive image. This is the archive, and you see it's other colors, and this is COLIBRÍ. So this is something new, and this has to be automatic. So in less than 5 minutes, we know if we find something. It's not trivial. Other thing that we are able to do is the distance. How I knew that this event that I presented before was too far. Okay, we don't have don't have a spectrograph yet. So, but we have 5 optical bands. It means that we can compare the flux in every band, in every filter, and to have an estimation of the distance. Our error bars, the COLIBRÍ sensitivity is good enough to have an excellent estimation that only differs like 10% of the spectroscopic redshift measurement that typically takes hours. So we are able not only to see new events, no, to just find new counterparts, but also to make an estimation in distance. And again, this is done in less than 5 minutes automatically. Let me talk about GRB, because GRBs are one of our best friends. So typically, what we want, or at least in my dreams, what I want to catch always is something that I know the distance, and if I can relate it with a galaxy, that is great, because I know the properties, the environment, where it comes from, and this was an ideal case. This happened 1 month ago, and Ramandeep and me we are working on this event right now. So we found this optical counterpart associated with this blue galaxy. And if you see, this is COLIBRÍ, and this is 5 days after the explosion. This is completely crazy bright, because if you remember the first slide, the brightness was fading very, very, very quickly. So why this is too bright? And the distance is not too close. There has been something there. And if you see, this is the archival image, it's not in there. So what we are doing?
Why did you wait 5 days?
Because if I make this figure for the paper, because if not, it was invading the galaxy.
But yes, you observed since the first.
Yes. Yes. So we have observations with COLIBRÍ. We have observations after 3 days, and let me, in a moment, I'm going to explain why. But we continue monitoring. Even 1 month after, we still detecting it. You see, these are the observation of this morning. And at the beginning, okay, we didn't expect to see something so bright.
What
So,
do you mean today? Today?
yes, this is
Okay.
this is the observation of yeah. So at the beginning, we didn't know what kind of object was. And if you see here, I put a probability map. Yes, this is a probability map because the universe is not so kind always. So what we receive, depending on the instrument that triggers the event, is a probability map. So the instrument said, look here, good luck. And you see this between the center and here, there are 7 degrees. Field of view of COLIBRÍ is 26 arc minutes. So this is not trivial for a standard telescope. We complement our observation in this case with telescope, with large field of view telescope, or that is called DOTI, that is also in San Pedro Mártir, and is collaborating with COLIBRÍ. So, but COLIBRÍ started 3 days later, which is not a problem in this case, because the event, if you see, there are not offset, there are nothing. So the event is what is very, very bright. You see the magnitudes is around 18, 17, and now today is around 20. So at the beginning, the question, and we were, and typically this is where Ramandeep enters in the collaboration, because okay, I put the data and Ramandeep put the interpretation. So what we are observing here, and first we want to classify everything. So what kind of series is this? And more important, and for me, I spent more than 1 week to understand if this was linked to this, because okay, I said not necessarily could be linked, but at the end it was linked. But then, so we compare with the population of the GRBs. We know that GRBs are produced typically for massive stars, and the duration is a very good clue about the nature. So typically, in average, if you see a GRB, is produced by the death of a massive star. And in a minor percentage, it could be produced by a merger of neutron stars. So at the beginning, we didn't know because the distance was too close to us. So this pointed more than a binary, a merger of 2 neutron stars. But with observation in the last days, if you see fading, and then flat. And you see in G is green, of course, and green is still fading. But what is happening in rudder bands? So R, it seems that it's flat, or at least not fading with the same rate, but C is increasing. So this means that we are looking other components, and we found that this is this is the evidence of a supernova. So now we know about the nature, and we can link this with the death of a very massive star. And this is, again, because I put the data, and then you have to model and you have to understand what star created this. And COLIBRÍ was formed to include the expertise and the experience of a lot of persons, Mexican persons, that have talent in modeling and understanding the transient sky. So just to mention the person that are here in the area, of course, Ramandip, Edilberto, and in Mexico City, Diego López Cámara, Enrique Moreno, and in Ensenada, Noemí Globus. There are other postdocs and students that they help us not just to see points, because I like to see points, but to understand what the points means. So in COLIBRÍ in Mexico, we are 12 persons, and most of them are theoreticians. So this has been a very excellent group, and the idea to integrate not just the observers, but also the theoreticians, and the theoreticians are learning how to monitor the telescope. Yes. Every person here now know what is a magnitude. That's amazing. And now how to point in case that we need to observe something that is not point automatically. They know how to use the telescope to take data in real time. So, and other, because as I showed you, there are a very big variety of transients right now. And, let me see, yes. So, there are other objects that we don't know what they are, but we know that there are blue. So, they are fast because they are transient, they are blue. We observe in optical and they are transient. So without any imagination, we call them fast blue optical transients. So we know that these events can be produced by the tidal disruption events, a gamma ray burst, a shock breakout. And we know that the light curves are typically very, very, very bright in optical, in ultraviolet, and in radio are quite particular. What is funny is that every transient is called by the discovery date, putting the year and also some letters. These letters, for some reason, are related always with animals. So this is, for example, we have the cow, we have the koala, and we have the camel. That's a very funny coincidence because there is no reason. So, for example, we observe this, Ramandip, other persons, these are very interesting events because I said, we don't know exactly what they are producing. So, we had an alert saying, okay, we discover something that in magnitude, in flux, putting at the same distance, is very similar to these events. So, of course, we automatically start our observation campaign, We obtain a lot of data and we compare. And at the beginning, we were very excited because we said, we have something very interesting. And I said, of course, because this is my quack, like a dog. It has to be a dog. So then the fading was not the same. And you can say, okay, but it's not very different. But these are very standard events. So, okay, I say, okay, maybe just a little bright. Maybe it's a blue dog. No. And then it was flattening. I said, okay, maybe it's another very different dog. And no. So at the end, it was a cataclysmic variable completely unrelated with this. But with our observations and with the campaign that we do after some days, and this only takes 5 minutes per night, we are able to confirm or discard scenarios.
5 minutes per filter. Per filter.
We observe there are 5 filters. G, R, and I are in one channel, C and Y in other.
So simultaneous observation.
Yes, so we typically need only 15 minutes. And finally, I think this is the last one. I'm going to talk about our first result that was published by my student, Camila Angulo. And as I said, there are other channels to produce this kind of explosion. And one of them is the collision of 2 neutron stars. So what are they so popular right now? Because of the gravitational waves. We are completely crazy about found some or discovered something related with gravitational waves. So this is the channel, and we expect to see an electromagnetic counterpart, gravitational waves, of course, and sometimes later the kilonova. The kilonova is this spherical component that appears after. So these are neutron stars, rotating, collision, relativistic jet, and here you see another spherical component that is called kilonova. It produces a lot of heavy elements like gold, thorium, europium, and others. So these are the responsibles of the interstellar medium enrichment in a very high percentage. So what we did is, so COLIBRÍ catch the first light after less than 100 seconds of this explosion. So at the beginning, we didn't know what was the nature, what was happening. We didn't know anything. So we observed automatically. So, but again, this could be related. We checked the properties of the old explosion, and we saw that this was very similar to what we expect for the merger of 2 binary neutron stars. So what we did is we asked also for X-ray observations. Radio is a radio, and we see the typical fading, and then we see something that is not, it's too soon to see related with a supernova, but it's too bright to see related with a kilonova. So what Raman proposed, it was that the central engine that produced this neutron star merger repowered the jet in some way that was able to produce this rebrightening or excess. So this is the first time that we get an event like this. And more important, and this is why the paper was so famous, that these events are very quick. And we were able to get a spectrum. This is a VLT, the X-shooter spectrum that I took. during the first day. The event was very bright, not common, but very bright, that we were able to take the spectrum. And this was not only to check the lines, how is the environment, how is the star formation rate, but also because this particular event was placed between two galaxies. So when I saw the image, why I don't know. So this was G1, it was 0.3, a redshift 0.3, and G2 it was 0.76. So with the spectrum, we were able to discriminate because the probability of association with both was very similar. Statistically, the GRB could came from any of them, but with the spectrum, we were able to make a right association. So, and this is not common. This is one of the few spectrums of a merger of two compact objects, and we have it. So, the last one, because I was learning about this 2 weeks ago. So, before a supernova explodes, and because we know what happened when a supernova explodes, there is something that is called supernova shock breakout. So, when the shock faces the star, the surface of the stars, the explosion is produced in the center. So at some moment it has to come out. At the moment when the wave see the surface of the star, it produces a very bright and short X-ray flash, and this is called supernova shock breakout. So this is very, very difficult to catch because you need to have the right detector to see, to catch this kind of light, and in a very short time. So this was March 21. So Einstein group, that is a mission that is operating right now, found one of these in a very close galaxy. And immediately, COLIBRÍ started to point. So we have, it's impossible. We don't have the shock breakdown, unfortunately, because it's only seen in X-ray, and the time that takes to report and to send information is more than 1 second, unfortunately. But COLIBRÍ started to observe since the first night, and we have all the light curves. Again, these are the data of tonight. So you see, we see since the beginning how the supernova is forming, and we have also information in X-ray, and we are preparing a publication on this image. So. So at the end of this talk, I wanted to talk about the strategy, some of the ideas I shared before, but what we want to do. So every event or object that is interesting for us, we observe it for the nights in which are detectable. And it means that we have a signal to noise ratio more than 3. These are our criteria. Something that is a very good idea from the PIs, it was that there is always someone in the telescope monitoring. They don't have to program anything, or almost anything, but it's a person who is checking every 15 minutes that there are nothing new that is not observing, that they are not, I don't know, we don't have another information, extra information that we have to change the filters, want to analyze something very quickly. So we have shifts between 8 p.m. and midnight. We have a Mexican shifter, and after midnight, Mexican midnight, the French person wakes up and is stopped. So, as I said, we have an automatic data reduction. So it means that you don't have to do almost anything. And this is during the night. And during the day, this is typically my job to check what is the environment of our events, if there are some galaxy close to them, to check what kind of nature could be, what kind of progenitor can be producing this particular event, because we typically will see there is an explosion and that's it. We don't have more information. So what we have to do is to analyze how the light curve is behaving, to have an idea of what is producing. So, and then we decide to collaborate with other groups, or even in the night, if we want to use a bigger telescope to take spectroscopy. So we have a very huge variety of solutions. So at the end, because this is why I'm here, we have what we do, because of course COLIBRÍ only works in optical, but all these events are typically triggered in gamma rays, X-rays, or ultraviolet, because they are very energetic. So, and if not, we can ask time by time of opportunities. I frequently do this to complement our light curves. And we have time in several instruments, GTC, VFT, Subaru, to complement our light curves. However, there is something that is missing in our group, and we don't have radio. Radio is essential for us because with the radio information, we typically can discern between the radiative process involved in this kind of explosion. So we can constrain or to say something about more the nature of the material involved in the jets if we have radio. And community is not very used to observe in radio. So the difference with radio is that we don't have to rush to take images. Why? Because high energies decay very fast and disappear in seconds. Optical in seconds to hours. But radio appears to emerge after 1 day, 2 days. So it's very different the strategy that we want to use. And this is the commercial and the marketing, because I know that this is an institute that is related with this wavelength, with frequency. So one of the parts of my job and my interest, if I have to say, is to complement or to have people interested to observe as part of the group, or have collaborations with persons that are interested to observe specifically with IRyA, that is the telescope that we miss. So the submission of proposal is in 2 weeks. So if someone is interested, please let me know. I will be very, very happy to work with some of you to prepare a proposal to explore the transient objects that we typically observe. And of course, all of you will be invited to the proposal. And as I said, you don't need to rush. So we only need to trigger, and then we have all the time to reduce data, to check weeks, not weeks. So please let me know. And the conclusion for the talk. So COLIBRÍ, even with a small size, is dominating the transient sky. And we are the leaders right now in the observation, detection, an identification of optical candidates. If you are interested to use COLIBRÍ, but you don't want to be involved in transient because it's too stressful, you can also ask time via CAT. And in Mexico, we have 40% of the time for the Mexican community. And if you are interested to be close of the collaboration, we have a lot of persons involved in Mexico and other 12 them in France that are expertise in all the transient events that we know that exist right now, and not just since the observational point of view, but also like numerical observations, theoretician. So we have a very good mix of what we can achieve. We have weekly discussions, and if you're interested to join the collaboration, it means that you are going to appear in other publications of the consortium. And we also have access to other facilities. In the future, we will have polarimetry. This is in the commissioning phase. So COLIBRÍ is going to be much stronger because of the polarimetry. And also the French part of the collaboration is finishing the proofs of the near infrared instrument. So we are going to be able to have photometry, polarimetry, and complemented with multi-wavelength time in other facilities. So if you want to be part of a collaborative and friendly group, please tell me. Thank you very much.
Very nice talk. Time for questions.
Yes, I have a question about when you see these stars very far away from the host galaxy. How are those stars going so far from the galaxies?
Which
they run away, and you see a point very far away from the galaxy, like this in the optical. So you have the galaxy and you have the supernova. How is that star going so far? Like,
excellent question. Yes, this is a model that proposed William Lee 20 years ago. So the idea is basically you have two neutrons that are rotating, collapse. And because of the gravitational force that is involved, there is a gravitational kick that expels the remnant out of the galaxy. And we know, this is another proof that typically we don't find this inside a galaxy.
How fast is the photometry per observation? And I'm asking this because some of these cataclysmic variables in symbiotic systems, they study the variability to search for this flickering effect. I don't know if you can do that. And it takes seconds, sometimes or minutes.
The shorter exposure that we have tested is 20 seconds, but we can do something more shorter, depending on the
very bright intervals. And my other question is, are you ready to observe this recurrent nova object, the Corona Borealis, who is expected to explode like 2 years ago?
I don't know.
Okay. So it's a recurrent nova that it's supposed to be exploring since a couple of years ago, and it will be very bright.
And it is the money.
It will be very, right now it's very bright. It's close, it's 200 particles.
What's money?
I don't know. It will be very bright.
Yes, it has to be 1 second exposure.
So right now it's unstable because the DC is over the
Yes, so we also observe cataclysmic variables of some persons that are interested, but they are very much fun.
Yes, please.
To do photometric in spectroscopy, you have two different instruments. It is like the same?
We don't have an spectrograph, no. So we only have photometry in this moment. What we can do is, again, if you are interested, or where, yes. So what we can do is comparison between how an event behaves in different filters, and we'll have an idea about the distance using photometric redshift.
Did you present a slide that?
Yes, but this is BLT.
Okay.
Yeah, this is why it's so beautiful. This one, right?
Yes.
Yeah, no, this is section.
No.
The question. Regarding this IRyA that you were mentioning a lot, so I guess you get the alert from gamma rays, and you get a huge area to search for. But how long did you take to find this optical counterpart that you found?
Depends on the event that triggered the explosion. So in this case, it was SWIFT, and SWIFT provides 30 half degree of precision, but then automatically starts to refine the position with the X-ray data. So when we are moving, because we receive the first position in gamma, the instrument is acquiring X-ray data, and at the same moment is arriving new information to refine the position. So in this case, we were very lucky because it was less than 10 arc seconds. So we didn't have to map.
Well, I think I'm meaning the other one, the one that was. Yeah, that it was like, I think you said 7 degrees away or something.
Yes. Yes.
So for these cases, how long do you usually take, or how much time? Because for me, it's very surprising that you find it in the first night, as you said.
I was not prepared, but I know this. So this is the other telescope that we have. So this is called DOTI, and we have 6 telescope mounts in the same mount. So we can cover 70 square degrees, so 69 square degrees per exposure. So it means that with every telescope we can catch 49 times the size of the moon. So it's amazing. So what we typically do is we map these very large regions with telescope like DOTI, and DOTI found the optical counterparts, and then send the information to COLIBRÍ, and we complement the observation.
Very nice.
Do these groups that report the transients also report the disappearance of a star? You know, there are these cases where a star sort of disappears and it's not clear what's going on. So that would be also interesting.
Yes, this will, yeah. I remember that in Andromeda 1 year ago, this was published a case of this. I think that the difference would be the cadence only, because we need to be mapping something to check if something disappeared or not. But yes, this could be interesting. I don't know where to look for, but a very interesting idea. Thank you.
Question?
The data from COLIBRÍ are cool. Do you have any archive or?
We are 20%. No. So the best way is to contact some of us if you're interested to have an observation, or if you know that was something interesting and it was visible from Mexico. Typically, we have them. So in that case, send an email, and of course we can. Yes. We are not so fancy.
I saw another hand raised. Some questions? Okay. Well, in that case, let's try to looks like it.
Zoom.
I think there's a after event already scheduled. So please join Rosa, and if you have more questions, we should be able to. Thank you.